Hello everyone, this is my day 4 of this challenge, and in this particular video I am going to solve the 7 problems of the basic math problems. So we will be just discussing every problem along with the approach and also the code of that problem. So firstly, let's get to the first problem, that is count digits of a number. This is the problem we are solving. See? And in this problem, what the approach we can think of, that I have to count the digits of a number. So just take a digit here, sorry, a number here, that is 123. And now to count the number of digits, we can either start from the first digit or we can start from the last digit to count the digits. Like we can think of that, if we can try to remove the digits one by one, and then we can count the digits in a number. So now if I try to start from the first digit, then what the case will happen? I'm trying to check for the digits from the start. So in that case, what I will have to do is that I will have to first know the place value of the digit, and after getting that place value, then only I can if I have to remove this, what I can do, that I can take the place value, and after having the place value, I can just perform the modulus of operation with that place value of this number, so that I can remove this first digit. But in order to get the place value, I will have to firstly know that the number of digits, what the number of digits are present in this entire number. So firstly, I will have to get the count of the digits, count of digits in number. So after getting the count of digits, whatever the count of digits is coming, let's say it is coming any n number, the count of digits. Then in order to get the place value, I will have to do 10 power n minus 1. So in this case, at the count of as the count of digits is in nums is 3, the place value will come out to be 10 power 2, that is 100. And so it means the 100 is the place value for this first digit. Now we have got the place value. So now what we can do is we can perform the modulus operation of this 123 with this 100, and we will get the result as 23. So it is the remainder after getting this, after performing the modulus operation in this. So we are getting 23. Now what we have done is we have just removed this number and got this end digits, that is 23. This is how we can say that we have counted the first digit, and just repeat this process. But the problem is that we have to know the count of the digits in the nums, and that's the problem. That's completely logical, because we are solving the problem for count digits in a number, and we must know that what is the number of digits present in the nums. That doesn't make sense. So we will have to start from the end digit in order to count for the number of digits inside the nums. What we will have to do is, the approach is simple, that we have to start from end digits. What we will do, we will just go at the end digit and start removing the end digits one by one. We will just remove the first digit, that is 3, and then we will just increment our counter. Then 2 will be removed. Here the counter will be incremented, and then 1 will be removed, then the counter will be incremented. And the moment the number just became as 0, we will stop there, because no more digits are left in order to count. So the simple thing is, we can just remove the digit. How? We can just divide this entire number by 10 again and again in order to remove the last digit. So what we are having right now is, we are having 123 right now, and if I am dividing it by 10, I will get as 12. If I will divide this 12 by 10, I will get 1. And if I perform the division of 1 with 10, it will give me 0. So the thing I want to say is that the number of divisions by 10 we are performing, that number of digits are present in this input. So the thing is that number of divisions equal to number of digits in input. Okay, so whatever the number of divisions we are performing, that number of digits are present in the input. That's the thing we have to do. Simple. Let's just come to the code and write it here. That firstly we will be keeping the counter for the number of digits as initially as 0, and now we will run a while loop, where the moment number becomes 0, I will stop there itself. The point, so for the number for the points where the number is not equal to 0, we will just run for that, and every time we will be performing this division operation on the number in order to shrink the number. So I will get this number equal to number by 10. We will just shrink, and every time we will just increment this counter. And the moment this number becomes 0, we will just decrement, we will just stop there. And at the end, we will be returning this counter. Will be returning this counter as the number of digits. So now, if we try to run this code, uh, let's give the input here first. And run this code. So it will just ask us for the input for the number we have to count the digits. So let's give it 123. It is saying that 3 digits are in the number 123. Let's run it for the another input. So and from the next video I will just keep a simulation for the number of test cases which I can run as number of test cases I want. Then let's give the input as 5050, that is giving me 4 digits inside the number 5050. So this is all about this particular problem. And just if we want to check the time complexity of this, so it is running a while loop, and inside this, that this number is dividing is just dividing by 10 every time. Every time it is getting divided by 10. So because of this, it is reduced by the by 1 by 10 every time. So that's why, because of the reduction is happening, so it is basically running in the logarithmic time, we can say. So that is the time complexity is it is leading to time complexity of, that is figure of log base 10 is log n, that is of base 10. I can is the logarithmic of base 10. That's the time complexity it is having. So that's how we have solved the first problem, and now let's get into the second problem. That is a reverse number. The reverse number problem, and in this particular problem, firstly take a number that is like 456. We have to reverse this particular number. Now how we can reverse this number is that firstly we can think of that if I can know the place value where I have to keep every digit. Let's say I have taken 6 firstly, then where I can keep this number 6, I can keep this at 100th place value. Then I can take this 5, I will keep at its position 10th place value. Then I can take 4 and I will keep at the ones place value. So it means I must know the place value of it, and in order to get the place value, firstly I must know the count of the digits, that how many digits are present in the number. Firstly what I am doing is I will just take this number digit, or sorry, I will just take this digit 6, and I will have the place value where I have to keep it. So let's say I have to keep this in, I know that what is the count of digits, and I know the what is the place value, so I can just take its place value, multiply it with the place value, then I will be getting 600. So this 600 will be kept in some any, let's say I will be taking a number which I will be returning at the end as a reverse number. So I will be just keeping inside the reverse num, let's say. So as of now, let's say I have just kept inside the reverse number, reversed num, that is currently 600. I have kept it inside this. Now next time, whatever the new digit will be coming will be added inside this reverse num. The new digit is 5. Now this 5 is taken and it is multiplied with its place value where it has to go. It will become 50, and now the result will become 650 inside the reverse num. Again this 650 is there, and now next digit, this 4 is coming and it has to go at its ones place value. Now there will be kept some of the counter or something in order to keep the track that the moment we are not having any place values left, then after that we will not be keeping, after that we will not be reversing, because at the end, when that particular counter is becoming 0, then the original, the input which is already given to us, that has already been reversed. So at the end this 4 will come and will be just added inside this. This will become 654, and that's the reverse number which we want. 456 654, that is the reverse number. So we just have to know that what is the place value of it. So let's just get into the code part where the reverse number we have to write. This is the code part, and here let's write the code for the count firstly, because firstly we should know the count of the digits. So initially we are having this count as 0, what we just did in the previous problem, and inside this we will just run a loop while, and until this number is not equal to 0, and we will every time divide this number by 10, and every time we will be implementing the counter. So this is giving me the count of the digits. Now after having the count of the digits, I will have to get the place value. So what we know, that whatever the count of the digits is there, let's say the count is for this particular number is 3. The number of digits are present here is 3. So what will be the place value for the uh, first digit from the left? So that is 4. It will be having the place value of 10 power that count minus 1. So if the count is 3, then 10 power 2 is the place value. So here I will just see what happened is that I have taken this number and I have just make some of the alterations in this number. So before doing this, I will also have to keep the original number, original num, particular number I will have to keep inside this original num, so that whatever the alterations I am making here, that should not that should not make that should so that I can whatever the original number is, if I am keeping that number inside the original number, and now whatever the changes I have to make, I can make easily. Now I have taken this reversed number equal to 0, because I have to add every time in this. Now what I will be doing, I have already taken this original number previously, so I will again initializing this number with the original number, and now I will be running a while loop until this count is greater than 0, and the moment it becomes 0, I will just stop there, because at that point I have already explained that if the count is becoming 0, it means the place values are not left, so I cannot do the further process, because at that point the number has already been reversed. So now I will be running this loop for count greater than 0, and every time I will be just taking out the modulus of this modulus number equal to, okay, I will have to just take the digit here, and digit equal to this number what I am having, this number modulus of 10, and whatever the digit is coming, I will just take that digit and multiply it with the power of the 10 power count minus 1, so that I can add inside the reverse number. Now this reversed, okay, I have taken this reverse number, this is reverse number, and this reverse number equal to reverse number plus reverse number plus whatever the digit I have taken from the previous line, I will be multiplying it with power of 10 power count minus 1. Count minus 1, why? I have already explained that whatever the count we are having, if we have to find the place value for the first number from the left, we will have to take 10 power count minus 1. If 3 is the digits, then 10 power 2, that will be 100th place value. Count minus 1, and after doing this, I will also have to shrink this number, and for that I will be dividing it by 10 every time, that the last digit gets removed, because for that last digit we have already added inside the reverse sum. Now this count will be decremented. Why? Because for this count, for this 3, I have taken this 3 minus 1, so 10 power 2, that is the place value. Now next time 10 power 1 will be there, so for that the count should decrement, the count will become 2, and then it will be decremented to 1. So that's how the count is decrementing, and at the end we will just return this reversed num. This is the code for this. So let's just try out a simple run for the example, that we are having the example 456. So firstly we have counted the digits, that is 3, and now the reverse number is 0 as of now. We will just have to take the sum for it, which will be giving the reverse number at the last. The original number we have taken, and now we are again taking inside the num, because we have made some of the alterations in this number. So now the counter is as of now 3, so 3 greater than 0, condition is true. Then the digit we will be taking, for the first digit taken from this 456 is 6. So now the 6 will be firstly multiplied into the power of this 10 power 2. because 3, so 3 minus 1 2, so 10 power 2, that will be 100. So 6 into 100, that will become 600, and inserted inside this reverse number. Now that number got shrink and number became now 45, and then counter is decremented. So counter is decremented from 3 to 2. So again 2 is greater than 0. Okay, so again the new digit is taken. New digit will be 5 in this case. So 5 is taken. Now 5 into reverse number is already what, 600, and plus this 5 into 10, what will be the power? Counter is now 2, so 2 minus 1, that is 1, so 10 power 1, that is 10, and this 5 into 10, 50. So now it will be added in 600, that will become 650. Again this number will be shrinked and it will become what? It will become 4. So 4, and now counter is decremented from 2 to 1. So now 1 is greater than 0, condition 2. Then the new digit is taken. New digit is already left, that is 4. So now the reverse number is already 650, and now 4 into the power of this 10. So now 1 is already there, and 1 minus 1 is 0, so 10 power 0, that is 1. So 4 power 1 is 4, and then when 4 is added in this, the 650 becomes 650 plus 4, that is 654. That is the original answer which we want, that is the reverse number. So that's how this code is working. And if we see the time complexity of this code, so again we are performing these number of divisions by 10 every time. So because this number is getting degraded by performing 1 by 10 every time, so for this the time complexity again goes to big O of log n. Okay, the logarithmic time complexity. But we can also do one thing. Let's just comment out this particular code, and in this what happening is we are just seeing the place values for every time. Like we are checking for the place values by ourselves. Like firstly we will be going with the 100th place value, then we will be going with 10th place value, then we are going with the ones place value. That's what we are doing, that we are every time we are checking for the place value, and then we are putting that as a sum in order to get the reverse number. What we can simply do is that we are having this number 456. Now what the reverse number will be? 654. What if we can take every digit and then shift it to the left in order to make the place for the incoming digit? So let's say I have taken the 6 initially, and now what I will be doing is when the next digit will be coming, I will be making the place for that next digit to come, so that it can sit at the place of the ones place value. So now initially I was already having 6. Now what I will be doing is that when 5 is coming next time, I will just make the place for that 5. So what I can do, I can just multiply this particular initial value which is present inside the reverse number. I will multiply it with 10, so that it becomes 60. And now when I will add this new number, that is 5, so that 60 plus 5, it becomes 65. See, I have made the place for this new 5, and now whenever this new number is coming, now 4 number will be coming, so I will just make the place for that 4. How? I will just multiply this already reverse number present, I will multiply it with 10, and now it will become 650. So now what will happen? When I will just add this 650 plus 4, so what it is becoming? 654. That's easy. Means whatever the number I am having in the reverse number, if I can multiply it with the 10, and after that after that I can sum the newer digit which is coming from the number, that means I am making the place for the newer digit to come at the ones place. So that's how I am making the number as the reverse number. Let's see the code part for this. So let's write code for this. So I was having the function initially, what, this reverse number, int reverse number. Inside this int number, and in this what happening is that I have to firstly keep the reverse number as I was doing, and every time I will be multiplying it with 10 and then adding the newer digit. So in this I will firstly keep the reverse number, first number, this is reverse number, and in this firstly initializing with 0, and then I will just doing the same thing, that I am having this number, and the moment it becomes 0, this loop will stop. And for every time I am taking this number and taking the digit of it. So int digit, that is equal to number modulus of 10. So it is giving me the digit every time. Now the moment I got the digit, I will just take this reverse number and keep the sum of it. So reverse number equal to reversed num. Now into every time when new digit is coming, I will firstly multiply it with 10 so that I can make the place for the newer digit, and then I will just add that digit so that the newer digit comes at the ones position. Okay, and also I will have to shrink this number so that next time it can perform the process, same process, and at the end the result will be the reverse number. Reverse number. Now let's just try to run this code. Okay, so firstly it will ask me for the input, so I will be giving the same input 456. 456 the input and 654 is the output. Okay, so again this also every time it is also like finding the remainder, but also dividing by 10 in order to get the remainder. So the it is again having the logarithmic time complexity. We write the time complexity for this as well. So both of the code we have written, both the approaches, they are taking the log n time. That's only for the smaller code, because in this we were having just finding the count of the digits and then we are solving. In this we can directly do this. Okay, so this is the just a shorter approach we can see, but both are taking the logarithmic time complexity. Okay, now second problem we have solved. Let's get into the third problem, that is the palindrome number. Okay, so this is the palindrome number problem, and in this what we will be having is firstly let's see what is a palindrome. So palindrome is uh, a number which we read from both the end. It is same like 121. If we read from this end, left hand, or from the right hand, it seems to be same, and it is same. It's just like a word. If we are reading or pronouncing from the left or right, it sounds same. That is a palindrome. So palindrome number here 121, from the left or right it is same. So now how we can check if a number is a palindrome? It is simple that if the reverse of the number is coming same, then the number is a palindrome. I will firstly find the reverse number, and after that whatever the number is I'm having input as an input, that is the original number. If both are same, then the number is a palindrome. Simple. So just write the code itself that I have to check the palindrome. So this is the check palindrome. In this firstly I will be just doing the same thing. I will be firstly doing this, keeping the reversed num as 0, and then I will be finding the reverse. So for that I will be just running a loop, whatever I have did in the previous that program in the code, that number is not equal to 0, and the moment it becomes equal to 0 I will just stop, and in this I will just take out the digit by digit from the number, this number modulus of 10, and I have taken the digit. Now I will be writing this reverse num equal to, I can write plus equal to reverse num equal to reverse num plus the, okay, I will have to do here reverse num into 10, and after that I will have to add that digit, and also I will have to shrink this particular number by dividing by 10. So this is how I am getting the reverse number. Okay, and because I am performing this operation on this particular number, so as of now the number is, as of now the number became as 0, then only the loop will stop. So now with what I will check this reverse number, so I will have to keep this inside the original number. So int original number equal to number, so that I can check it later in returning. Now at the end I can just write this statement that return original num equal to reversed num. Okay, so here what I have done is that I have found the reverse number, and whatever the reverse number is, if it is equal to the original number, then that number is, sorry, then that is the condition is true. because both the numbers are equal. That means it is a palindrome. Otherwise, if the reverse number which came that is different from this, it means both are not equal. So so then it is going to return false. Let's just run this. It will ask for the input. So I will be giving the input as 121. 121. So yes, 121 is a palindrome. Now again, check for the time complexity. So again, the time complexity is coming same, that is the logarithmic, because again it is dividing by 10 every time, and it is decreasing by 10 every time as the number is dividing by 10. So again, the time complexity is going to be logarithmic. The time complexity for this I will write just here. Okay. So we have also seen this particular program. Now coming to the most important problem, that is GCD. In order to solve this problem, we have this, that if I have to find the GCD of A comma B. Okay. So what can be the first approach? That if I have to find the GCD, firstly, what is the GCD of any two numbers? So GCD is a greatest common divisor, or I can say the highest common factor, or in most simple terms, the largest number which is common to both the numbers. See, let's take the example. If I have to find the GCD of let's say 18 comma 12, 18 comma 12. Now the largest number which is common in the divisors, whatever the divisors are for 18, whatever the divisors are for 12, the largest common number which is dividing both the numbers, leaving the remainder as 0. It means dividing both the numbers completely, it means leaving the remainder as 0. So that is the largest common number, that is the greatest common divisor, that is the GCD of these two numbers. So let's firstly have the divisors of all the divisors of 18. What will be the divisors? That will be 1, that will be 2, that will be 3, that will be 1 will be the divisor of both, 2 will be the divisor of both, 3 will be the divisor of both, 4 will be the divisor of 12 but not for 18, 5 will be the divisor, it will not be of any, then 6 will be the divisor of 18 and 12 both, then 7 will not be, 8 will not be, 9 will be the divisor of 18 but it will not be of 12, and then so 1 is the divisor of 18 and 12 both, 2 of both, 3 of both, 4 is not, it is only for 12, 5 is not, 6 is for both, 7 is not, 8 is not, 9 is not, 10 is not, 11 is not, 12 is not, then 18 will be coming here. Okay. And if we are seeing the divisors of 12, so 1 will be the divisor, 2 will be the divisor, 3 will be the divisor. Okay, so here we are not seeing the commons, here we are seeing all the divisors which are available. So 6 is the divisor here, then 9 will be the divisor, then yes, 18 will be the divisor. Now here in this 12, 1, 3, 4, 1, 2, 3, 4, 5 not, 6 is the divisor, 7 not, 8 not, 9 not, 10 not, 11 not, 12 is the divisor. These all are the divisors. Now if we see here, then 3, then this particular 6 is the one which is the largest and also common among both the divisors. So the result will be like GCD of this 18 comma 12 will be what? That will be 6. 6 is going to be the result for this example. So because 6 is the largest and the common number which is dividing both the numbers 18 and 12, leaving the remainder as 0. That's what the example is. It's the result of this GCD of 18 comma 12, that is 6. So this is the simple approach which we can follow, that we can find all the divisors of this 18 and we can find all the divisors of this 12, and then whatever is the largest common one, we can simply return that number as a GCD. So in this, what we can do is we have to also keep in mind that whatever is the smallest number among these two numbers, we have to go or run the loop till that particular number itself, because till that number only we will get the GCD, the largest common number among both. So just think that if any number is greater than 12, it might divide this, but it cannot divide 12. And we want the number which is common and the largest among both. We have to just see till the minimum of both the numbers. So we will be running the loop till 12 only, or whatever the number is minimum among A and B. That's generalized. So let's get to the code part, and we will understand more from there. So this is the naive approach we are writing for. So firstly, we will have to calculate the minimum out of the both numbers. That is mini, the variable I am taking, and minimum of both the numbers A and B. Now I have taken the minimum. I will just run a loop for int I equal to 1, I less than equal to mini, and I plus plus. Now what I will be doing it, I will just be checking that if any, what is the number which is dividing both. It means leaving the remainder as 0. If A modulus of I is equal to 0 and B modulus of I equal to 0, then in that case, what I will have to do, I will have to maintain a largest divisor variable, and that will be initially as equal to 1, because as of now 1 is the maximum or the largest divisor possible for which will be dividing both A and B. And now when I have found that that this particular number I is dividing both, then I will update this largest divisor by that I. And at the end, what I will be doing, see, just run this particular program for this example. 18 and 12. As of now, my A value is 18 and B value is 12. Just check for this. What is the minimum out of this? 18 and 12. 12 is the minimum. So 12 is inside the mini. I have taken the largest divisor as of now, that is 1, because it is the maximum possible divisor, largest number as of now. I am knowing that it will divide 18 and 12 both, which will leave the remainder 0. Now I am running the loop from I to mini, that is till 12, because in this range only I will get my largest common uh, that particular value which will be dividing both. And then firstly 1 is taken, so 1 is dividing both, yes, so it will be updated inside this largest common divisor, that will be 1. Now 2 will be there, so 2 is dividing both, yes, so 2 will be updated. 3 is dividing both, 3 will be updated. 4 is dividing both, no, because 4 is dividing only 12, not 18. Then 5 will come, so 5 is dividing, no. 6 is dividing, yes, so now 6 will be updated in the largest divisor. 7 is dividing, no. 8 is dividing, no. 9, no. 10 is dividing only 18, not 12. Then 7, no. Okay, sorry. 9 is dividing, no. 10 is dividing both, no. 11 is dividing both, no. 12 is dividing both, no. And this loop will be running till 12, so 12 less than equal to 12, condition 2. But when 13 comes, there the condition goes false, and last time the largest divisor was updated with 6. So at the end, the largest divisor will come, the result will be 6. So now at the end, we have to do just the simple thing that we have to return this largest divisor. Now let's just run this code. It will ask me for two values in order to get the GCD of those. So here I will be giving the input as 18 and 12. 18 and 12, and it will be giving me 6 is the GCD of the of 18 and 12. GCD. And let's run it for the another example. Let's see. Another example is like we can take like 15 comma 25. So 15 25, this the GCD is 5. Okay, GCD of this 15 and 25 is 5. Now let's again check the time complexity of this. So time complexity of this code is coming out to be big O of this minimum value. If 18 and 12 are there, so it will be big O of 12, means whatever the minimum value is among A and B, till that will be the time complexity, that is big O of the minimum. Okay, so if we are writing here the time complexity for this first approach, that will be big O of minimum of a comma b. That will be the time complexity. But this is taking the time complexity of this. For the first approach, big O of minimum of a comma b. What if we can reduce this particular time complexity? And that's where comes the most famous approach, that is Euclid's algorithm. And in the Euclid's algorithm, what happens is, the Euclid's algorithm, what happens is that whatever the GCD we have to find, the GCD of a comma b, if we have to find the GCD of this, Euclid's algorithm says that if any number, let's say, if see, at the end a number is going to come which is going to divide both of these, which is going to be the largest common number among all the divisors which are present. For a while, let's consider that d is a number. If d is dividing, if d is dividing a and b, then d should also divide a minus b. That's what the Euclid's algorithm says. If we have to find the GCD of a comma b, then if d is a number which is dividing a and b, then it should also divide a minus b. Let's just understand it with a more with the example. So let's just take an example that we are having a number that is equal to, let's say, sorry, we have to find the GCD of what, two numbers. Let's say GCD of the same example, that's 18 comma 12 we have just taken for the first approach. So if we have to find the GCD of this 18 comma 12, I am saying that if p is a number which divides 18 and 12, what does this mean? Then it means if the d is any number which is dividing 18 and 12, then it should also divide 18 minus 12, also divide 18 minus 12. And if it is dividing 18 minus 12, then what is 18 minus 12 here? That is 6. Then should also divide 12 minus 6. What is 12 minus 6? That is 6. Then it should also divide, 6 minus 6. That is 0. That's what the Euclid's algorithm says. If any number is there, which we will be finding as the output, if it is dividing 18 and 12, it should also divide the difference of these both. Then whatever the value is coming, it should also divide this 12 minus 6 again. Then it should also divide this 6 minus 6 again. And the moment we are getting the 0 after this, all the subtractions, at the end, whatever the number we got, that is the number which is the GCD. Or we can also, just to have a better explanation, we can also add one more step, that it should also divide 6 minus 0, that is coming to be 6. So now whatever the subtractions you will be performing after this, here the 6 is going to be the number which is same. So that's the GCD of these two numbers. Let's just map it with the number. Here what is happening? Is we have divided this 18. What will be happening is, we are what we can write for this 18, that will be like 12 into 1, and when we add into, and then when we add 6 into that, it will become 18. Now next time, whatever this 12 is there, how it can be written, I will just explain in a while what is happening. This 12 is written, and now when we perform this 6 into 2, it will become 6 into 2 12, and the remainder left out is 0. And now when you take this 6 here, okay, what happening is, just see, here you have subtracted 12 from 18, so you got 6, and you have subtracted 12 only one time, and here you have multiplied 12 one time where you got the remainder 6. Again, you have subtracted 6 from 12, you got 6, and then you again subtracted 6 from 6, you got 0. And here you multiplied this 6 two times, and then you done the it's like you multiplied this 6 two times, you got the remainder as 0, because 6 into 2, that is 12, you got the remainder as 0. This particular remainder is nothing but the repeated subtraction. Whatever the remainder you are getting here, the 6 is the remainder, that is the repeated subtraction for one time of 12. The 0 is the remainder for the repeated subtraction of 6 for two times. That's what you are getting. And the moment you got the remainder as 0, the last divisor which you got, that is the GCD. The moment you got the remainder as 0, after that you will not be performing this particular process, because the moment you got the remainder as 0, the last divisor which you got, that is going to the GCD. Where what is happening, just generalize this particular thing. If we have to find the GCD of 18 comma 12, what it is going to happen is that you are performing this 18 and it is divided by 12. So 18 divided by 12, what the remainder you are getting, 6. Then whatever the remainder you are getting, you are taking this previous divisor, and again whatever the number you got here initially, you just divided by 12, you got the remainder as 6. Then whatever the number you have taken here, this 12, it is divided by the remainder which you got, and then whatever the remainder you got, it is 0. Now the previous divisor 6 was there, it is the greatest common divisor, that is the GCD. Here again what you are doing is that GCD of, firstly you found the GCD of this 6, you have just calculated the GCD of 18 comma 12, and after that what you are doing is, after that you are taking this 12 at the place of this 18. Firstly 18 comma 12 GCD, and now at the place of 18 you taken 12 here, 12 comma whatever is the remainder you are getting here, 6. You are dividing this particular 12 by that 6. So at the place of 12 you have taken 6, and now for this you will be again taking the GCD of what, the place where you are having the, you can just write in this form that whatever the 0 is you got here, you will take this number 6, and then what will happen, you have got the remainder 0. So 0 multiplied by anything, just think of as 1, just multiplying, sorry, what is the remainder, then you will be getting 6. Now this 6 is at the place of 12 here, 6 will be coming at place of 12, 6 will be coming at the place of 12, and whatever is the remainder, this 0 is the remainder, so you are dividing it by 0, 0 is coming here. It's just for the explanation part. So now whatever is the value coming, that is coming as 6 at the end. So one important thing is because that's the moment where this particular thing will stop. When GCD of any number, let's say a, or here in this case 6, is calculated, comma 0, GCD of 6 comma 0, it will be coming out to be 6. But let's just generalize it. GCD of this a comma b, GCD of, sorry, a comma 0, a comma 0, it will give us a. That's the important part here, and here the algorithm will end, where it will find that this particular b is 0. Now it will end this particular process, and from that point, because the GCD of this 6 comma 0 is 6, so it is indirectly going inside the value GCD of 18 comma 12, which is the output of this, the result. So that's the simple approach. That Euclid's algorithm says that if any number is dividing 18 and 12 both, it must also divide all the differences which are available, which will be uh, performed, and that will be the number which is the GCD. So this is how it is happening. That every number which is coming as the remainder, it is nothing but the repeated subtractions. So if you are doing the subtraction of one time, or if you are multiplying it with, like in the division method, it is coming out to be this. The moment you got 0, you will just stop there, and the divisor which is at the last, that is the number which is the GCD of these two numbers. And the moment you got this form, the GCD of a comma 0, then just return this a value. That is the last divisor, and that is the GCD, the number a comma b. That's the whole thing. And let's now just get into the code part. The Euclid's algorithm we are talking about. What we'll be doing here is we are already having this number. Now we want to perform the Euclid's algorithm. So to perform the Euclid's algorithm, we are already having this GCD. We have to calculate for this numbers. Now every time I will be just running this particular loop till the moment b is not equal to 0. Okay, and what I will be doing, every time I will be getting the remainder, like GCD of 18 comma 12. I will be getting the remainder, and whatever the remainder will come there, in this case the remainder is coming as 0. That remainder will be again taken in the place of what? It will be taken in the place of b. But before getting into the place of b, we will have to put that b value inside a. Okay, this b value inside a. So here firstly I will be getting the remainder, int remainder equal to, how the remainder is taken, a modulus of b. And I will have to I have to keep this particular remainder in b, but before that I will have to keep that b inside a equal to b, and then this remainder is taken inside b, done like this. And at the end, what I have to do, I have to just return this a. So let's just run this example on this code. GCD of 18 comma 12, a value is given as 18 and b value is given as 12. Here b is not equal to 0, condition true, 12 is not equal to 0. Now remainder, 18 divided by 12, what is the remainder? 6. 6 is the remainder. In this case 6 is the remainder. 6 will come inside the remainder. Now 6 has to come in place of b, but b value has to go in a first. What is the value of b? B is having the value right now 12. So 12 will go inside a, and the remainder, this 6 will come inside b. So GCD of 12 comma 6 will be calculated now. Now is this b not equal to 0? Yes, this b value is right now b. This 6 is not equal to 0, condition true. Now again we will be calculating the remainder. So remainder of this 12 and 6. 12 is divided by 6, so remainder becomes 0. Remainder is 0. Now b value is what? B value is 6. 6 will be going in a, and this remainder 0 will be going in b. Now the GCD will be calculated for 6 comma 0. Now b is not equal to 0. 0 is not equal to 0. Condition false. Condition goes false, and here a will be returned. That is GCD of 6 comma 0. That is 6. It will be returned. That is going to be the answer. So let's run this code. Asking for the input first. Input is 18 comma 12. Yes, 6 is the GCD of the number 1 and number 2, 18 and 12. And if you see the time complexity of this, the time complexity will be like, see, in the previous naive approach, what we were doing is that we were running a loop which is till minimum value. So that is the logarithm, that is the big O of the minimum value of the a comma b. So that was somewhat greater, but in this Euclid's algorithm, if we see, here we are running a loop which is running for this particular value, that whatever the, like, if we see that whatever is the initial value, it is just getting logarithmic, it is having a logarithmic time complexity, a kind of, means whatever the value we were having, this kind of decreasing in the in some number of steps. So whatever the number of steps we are given with, that number of steps are equal to the number of digits, we can say. So whatever the steps are performed, the bigger value is getting decreased by the number of steps. Just consider that if we are having a larger value, let's say we have to find the GCD of, like, a larger value, and we are given with this comma 2, we have to find the GCD of this. So how many number of steps will be required? Just one step, because this is divisible by 2, and because this is divisible by 2, the time complexity is just a logarithmic, we can say. because it is just for the larger number, and whatever the smaller value is present there, which is dividing the number a. If it is smaller, then in that case it is going to be, the number of steps are going to be logarithmic, uh, just decreasing. So that's why we are saying that it is having the logarithmic time complexity, because whatever the value we are given with, if it is decreasing with the minimum number of steps, and obviously it is, because we are every time if we see the number of steps are decreased by logarithmic performance, like that. That's how we are saying that the time complexity is going to be O of log, and that is big O of log of minimum of a comma b. That's how minimum of a comma b. So whatever is the minimum of a comma b of that log. So here minimum of a comma b is whatever the value is, that will be decremented in the logarithmic way. It means the number of steps required, that will be equal to number of digits. That's what that's how its time complexity is going to be big O of log of minimum of a comma b. Now we have seen the Euclid's algorithm as well for this problem, GCD of two numbers. Now let's get into the fifth problem, that is check if the number is Armstrong. So to check if the number is Armstrong, what what is the Armstrong number? Armstrong number is a number, whatever the digits are present in this Armstrong number of a number, if we do the sum of those digits by doing the power of the number of digits. Just see here that if any number is there, number is there, if any number is there, if perform the sum of all the digits taking 10 power number of digits. So if any number is given, and if we are performing the power of digits, like if we had whatever the number of digits are there, firstly we take one digit and take the power of 3. If any digit is having 3 digits, if any number is having 3 digits, then we take that digit power that number of digits, plus we take another digit and power that number of digits, that number. So after that, taking the summation, if the number is coming out to be same, then that number is the Armstrong number. Okay, so let's just go in the code. So what we will be just doing, if any number is there we are given with, we will be taking every digit, and firstly we will also have to take the count of the digits, then only we can do the power. So first we will just take the count of the digits, and then we will perform the number of uh, like sum of the digits by taking the power of that. Just that is the strong number. Here in this, firstly what we will be doing is, firstly we will be taking the count of the numbers. Int count equal to 0. Inside this, firstly we will be counting. So while this number this number is not equal to 0, we will be just counting the num equal to num by 10 we will be doing, and implementing this count. We have counted the digit as of now. We will also have to keep the original number it's at the start, because we have altered that number. Original equal to num. Now what we will be doing, we have kept this original number, and because we have altered the numbers, we will just keep this original number again inside our number, in order to make the later on tasks, the later task. Now I have taken the original number inside the num, and now I have to check this Armstrong number. So firstly I will be taking the sum as 0, and now taking the sum as 0, what I will be doing is I will just run a loop for this while when the number is not become equal to 0, till then I will run this loop, and I will take the digit every time. I will take the digit every time, that is num modulus of 10. I have taken the digit, and now I will take that digit, and inside that whatever the number I have taken, sorry, this is the sum I have taken. So inside the sum, now I will be summing up that particular digit. So the power of digit, comma, count, whatever the count I have taken. And every time I will also have to shrink that particular number. And at the end, I will just turn that whatever the sum I am having and whatever the original number I am having, I will just return this. Just return this. If these numbers are same, then it means it is a Armstrong number, so that it returns true. And if that particular number which I got as a sum, it is not equal to original number, then it is not Armstrong. It's all about this. And if we see the time complexity of this code, so time complexity again, I am again performing the number by 10 again and again, so that's how it is decremented. And the time complexity which is taken for this is, that is big O of log n. Again, for this, the time complexity for this code will be log n, the time complexity for this code. Now let's get to the another problem, the divisors of a number. This particular problem is going to help in the checking the prime numbers. So to get the divisors of a number, let's say I'm having a number 18 and I want to check for the divisors of this number. What I will be doing to get the divisors, firstly see what are the divisors of this number. 1 is the divisor, 2 is the divisor, 3 is the divisor, 4 is not, 5 is not, 6 is the divisor, 7 not, 8 not, 9 is the divisor, then 18 is the divisor. To get all these divisors, what we can do is we can just run a loop for 1 to that number, or whatever number I am doing, 1 to that number, and if whatever the numbers I am that is dividing, it means giving the remainder as 0, that I will be going to print. Simple. Let's just directly come into this and print all the divisors. So I am having this number n, and now what I am going to do is I will just run this loop. See, it is simple, and it is also suggesting, just check this. I am starting from 1 to n, and I am performing this modulus operation with high, and if it is giving the remainder as 0, I am going to print it. That is simple, and we can also see that the time complexity is coming out to be big O of n. But one more better approach is there. If I am performing this 1 into 18, it is giving me another divisor as 18. If I am performing this 2 multiply by 9, it is giving me another divisor as 9. If I am performing this 3 into 6, it is giving me another divisor as 6. Then after this, if I am going to multiply this 6 into 3, that's the same pair I got. If I am doing 9 into 2, it's the same pair I have already solved. If I am going to do 18 into 1, that's the same pair I have got. It means after a particular point of time, after a particular step, I am getting the same pairs. That is the reversed pairs. So in this, the catch is that if I can run a loop for till root n, it means whatever the number I am having, let's say I am doing for this 36 number, let's say number 36, and in this 1 into 36, if I do it gives me 36. If I do 2 into 18, it gives me 36. If I do 3 into 12, it gives me 36. If I do 4 into 9, it gives me 36. If I do 6 into 6, it gives me 36. And after this, whatever the multiplications I am doing, like for 9 into 4, it is already there. After this 12 into 3, it is already there. 18 into 2, it is already there. 36 into 1, it is already there. It means after this root n, for this 36, the root n is 6. After this root n value, all the pairs are getting reversed. So why need to check for the rest of the values? Because the previous values are already giving me the all the reversed pairs. That is 1, 2, 3, 4, 9, 12, 18, 36. Simple. So I can just run a, I can just write a simple code for this. Let me just comment it out, and what we can do is we can just run a loop this simple, whatever it is suggested. I know already that I can just run this loop for root n. And how we can write I, we are running this I less than equal to root n. So I will just do a square root of so thus I will just square at both the ends, and I will get I square less than equal to n. So I'm just running a loop till root of n, and when I will be performing this, I will be just seeing that if it is the remainder getting 0, so I will just print I. And also I will be checking that if I is not equal to n by I. How n by I? If I am having a number, let's say this 36, and if I am saying that currently 2 into 18 is giving me 36, and also if I do this number 36 by 18, sorry, by 2, it is giving me 18. So this is how I am getting the two divisors. One is I and one is n by I. So that's how why I'm checking here, that there may be the another number that is the square root itself. So just for checking for the square root itself, in that case it will print it two times. So that's why I'm checking that if I is not equal to n by I, then only, because I will already print it for 6, but here the 6 is equal to be n by I. So that's why for checking for the root n condition, I'm keeping this condition that if I is not equal to I, n by I, then only print this n by I. Otherwise, if it is equal, do not print it, because it will give the 2 times 6. That's why for the root n condition. So this is how the problem is solved. And in this, uh, if the first in the first approach, if we see, then it is running for big O of n time, but this is the more optimized version, that it is running for big O of root n time. First I'm running this loop for root n. So that's what the time complexity goes from big O of n to big O of root n of square root of n. That is the most optimized. This is the problem we have solved. Now let's get into the last problem, that is the check for prime numbers. This is the problem for the prime numbers. Now in this again the same concept is used, which we have used earlier, but that for the optimized version. For the prime numbers, if any number, let's say 41 is there, is this firstly, what is the prime number? Prime number is the number which is divisible by 1 or itself. Whatever the numbers are less, let's say 36 is the number which is divisible by many of the numbers, so it is not prime. But 41, it is divisible by 1 and itself, that's why it is a prime number. Now for this we will have to check for all the numbers from starting from 1 to, see, for 1, if we see any of the number, that any number is divisible by 1 in itself. But the important thing is that we have to check for the numbers starting from 2 till n minus 1. So for that we will have to check. So for this 41, if we check from 2 to 40, no any number will be there which is dividing 41 except 1 and 41 itself. So that's why it is a prime number. But if we check for 36, then for 36, 1 and 36 will itself divide, but also like 2, 3, these numbers will also divide. We just have to keep a track that if any number between 2 and that n minus 1 number is dividing, then we will just get to know that that number is not a prime number. So let's just go to the code part. It is a easier one. So check for the prime number. Here I will be just running a loop for this int I equal to 2, I less than equal to n minus 1, or I less than n, and I plus plus. and I just, and inside this, if this number, if this num or modulus of I, if it is giving me the remainder as 0, if any of the number, because 1 in itself is there, but if any of the number is giving me remainder of 0 from 2 to n minus 1, then I will just there itself return the false. Otherwise, if I am coming till the end but I am not getting any number which is dividing, it means it is only divisible by 1 in itself. That means I am going to return true. Just run this. Firstly ask me for the input. I have given, this is the num. In for the input, check that 41 is a prime or not. 41 is a prime. In run this code. I am checking for the number 36. 36 is not a prime number. And in this again, if we are checking for the time complexity, so it is again going to like big O of n. But if we have to optimize it, we can run this particular loop again for big O of, sorry, again we can run this particular loop till root of n, because in this again we will having the same thing, that if I am saying for 36, so I have as I have just explained here, that for 36 if we see, then after a particular point the pairs getting reversed, so there is no point of checking for all the divisors, because these all the divisors are coming before root of n itself. That's why we are not checking for after root n, so that our process, this approach gets more optimized. So we will be just checking for the till root n itself, and whatever the loop which we have written here, we will just run it for this. We will use this I square. This is num. So here, this is the simple thing we have used, that we are running this loop from here itself till root of n itself, because after that the pairs start getting reversed, so no need of checking for that. And if till this point, see, if any number has to divide that number, input number which we are given, it will be found under the root n itself. No need to go ahead, because even we are checking for ahead, the reverse, the pairs getting reversed. So if any number will be dividing, that will be found before root n itself, because all the pairs are available there. So this is the approach, and this particular approach takes big O of root n time complexity, so that the approach gets, so because of that the approach is more efficient than the previous approach. In this also, if you try to run this code and try checking if any number is prime or not, just put 51 here. 51 is not a prime number. And if you check for another number, let's say 93, 93 is not a prime. Now check for 41. 41 is a prime number. That's what this problem all about. And there can be some of the cases, like if we see in these numbers, like there can be some of the edge cases present, like in the count digits. If we see that I have just not explained here, if the count digits are having the, like let's say if we are checking for the 0, then in that case, if we try running this particular program for 0, then in that case the while loop will never be executed, and in that case this will give, this count will always remain 0. That will be invalid, because 0 is the number which is having one digit. So in that case we have to keep the edge case, that yes, if number is equal to 0, then we will return 1. And similarly in other problems as well, like there can be, like in the reverse number, there cannot be the, might be. And then checking for the palindrome, so in checking for the palindrome, let's say if the number is negative, so in that case you can take the absolute value, or not absolute value, I think in the negative numbers we cannot like negative numbers are not the palindrome. So if we are getting as any number is negative in the start itself, this number less than 0 means it is negative, then just return false in that case, because the negative number cannot be palindrome because of the minus character. Okay, then in the next problem, like the GCD might not in the when we are checking the prime, so here you will have to put one condition that if whatever the number you are given with, if that is lesser than or equal to 1, because zeros and ones are not numbers which are prime, so in that case you will have to return false. Okay, so because these numbers are not the prime, lesser than or equal to, you can put the edge case for this as well. Then for the Armstrong number, if you are given with any number which is like, if that number is 0 itself, then you can see that 0 is having one digit, and if you try doing like this 0 power 1, so that will come out to be 0. So in that case you will have to return true. Like, if you even may not write this particular case edge case, then it also works, but it works accidentally in that case. You can just try route running this particular code without this edge case. It will run, but it will run accidentally, so better to put that put this particular edge case explicitly, so that it works correctly. If the number is 0, the number of digits are 1 in this case, so 0 power 1, whatever the digit is taken 0, and then 0 power the number of digits, so 0 power 1, that will be 0 itself, so it will return true. So it means the Armstrong number, that if we are having any digit, any number, and if you are performing the digit sum power to the number of digits, then it gives the same number. So 0, it gives the same and it returns true. That's what it all about. And I've checked for all the cases. That's all for